Okay, this lecture is going to be over section 12.7. We're going to look at longitudinal standing waves. Now, when a longitudinal wave propagates in a fluid in a pipe with a finite length, the wave reflects and forms a standing wave. The closed end of the pipe is going to be a node, like there. And the open end is going to be considered an antinode. For an open pipe of length L, the lowest frequency with antinodes at both ends is going to be the fundamental frequency. And the harmonics are integer multiples of that. If a pipe is closed at one end, the fundamental frequency is basically half of that. And you can kind of see that here because with an open pipe, you have antinodes here. Basically, that's where you have the freest amount of movement of whatever's coming in and out. And here you have a closed end and then an open end. That's why that's 1/4 of a wavelength, and this is 1/2. So if a pipe is closed at one end, then the fundamental frequency is this, and the harmonics are going to be 135 multiplied by that. And so you can see here that the fundamental of an open pipe and the second harmonic is just going to be double that. You're going to have a fundamental here, and then you would have a third harmonic. You wouldn't have the second harmonic. If you did, you would end up with a situation like this, which you don't have an open end of the pipe. So you would have to introduce a full wavelength in there on top of what you already have. So let's go to the section, and let's just kind of take a look here and see what it has to tell us. There are some pretty interesting YouTube videos out there on this particular subject. The tube in particular that we'll get to here. So when longitudinal waves propagate in a fluid contained in a pipe with a finite length, the waves are reflected from the ends in the same way the transverse waves on a string are reflected. The superposition of the waves traveling in opposite directions forms a standing wave. When reflection takes place at a closed end, then the displacement of the particles at that end must always be zero. Just as with a stationary end of a string, there is no displacement at the end, and the end is considered to be a node. If the pipe is closed at both ends, then each end is going to be a node. And you may have nodes at intermediate positions within the pipe if you're looking at harmonics on top of that. If an end of a pipe is open and the pipe is narrow in comparison with a wavelength, then the open end is going to be an antinode, the point at which displacement of a medium is maximal. You can recall that a free end of a stretched string is also a displacement antinode. In other words, it's got the freedom to vary quite a bit there, and that's why they consider it to be an antinode. So the longitudinal wave and a column of fluid are reflected at the closed end and open ends of a pipe in the same way that transverse waves in a string are reflected at stationary and free ends respectively. So a closed end is always a node, and an open end is always an antinode. A standing longitudinal wave in a pipe always has alternating nodes and antinodes. The pressure variations in the pipe also have an alternating pattern. And it turns out that the antinodes correspond to points in which there is no pressure variation. And we can call these pressure nodes. So to distinguish the kinds of nodes, we sometimes speak of displacement nodes as well as pressure nodes. Hang on a second, I think I may have some issues there. Let's make sure this is recording. Okay. And similarly for the antinodes. A displacement node is always a pressure antinode, and a displacement antinode is always a pressure node. So they have an inverse relationship there. The relationship will become clear in the next section. So we can demonstrate longitudinal standing waves in a column of gas and also measure wave speed with an apparatus called a Kunz tube. That's for a German physicist. a longitudinal gas tube, a meter or so long, is closed at one end, and at the other end has a flexible diaphragm that can transmit vibrations. So you've got a speaker here, vibrations are submitted here, and then sounds of an appropriate frequency produce standing waves with displacement nodes and antinodes. And this powder that's in here will collect at the nodes. We place a small amount of black powder in there and distribute it uniformly along the bottom side of the pipe. As we vary the frequency of the sound, we pass through frequencies at which amplitude of the standing waves become larger or large enough for the moving gas to sweep the cork dust along the pipe at all points where the gas is in motion. The powder therefore collects at the displacement nodes where the gas is not moving. Adjacent nodes are separated by a distance of the wavelength divided by 2, and we can measure that. We read the frequency from the oscillator dial, and then we can calculate the speed of the waves from the relationship of the wavelength times the frequency. That is a neat little demonstration, and if you can find one out there on YouTube to talk about it, it'd be very, very interesting, I think. Normal modes. So many musical instruments, including organ pipes and all the woodwind and brass instruments, use longitudinal standing waves or normal modes in vibrating air columns to produce musical tones. So organ pipes are one of the simplest examples. So air supplied by a blower at a pressure on the order of 10 to the third pascals to the bottom end of the pipe, and then a stream of air is directed against the mouth of each pipe. So you can see that here. The column of air in the pipe is set into vibration. There is a series of possible normal modes, just as with stretching a string. The mouth always acts at an open end, thus it is a displacement antinode, which you can see right there. The top of the pipe may be either open or closed, an open pipe or a stopped pipe. If it's open, then you would see the antinodes there. If it were closed, obviously it would be a node. So here in this figure, 12.23, we've got 3 modes in a schematic organ pipe open at the top end. Both ends of the pipe are open, so both are displacement antinodes. The fundamental frequency corresponds to a standing wave pattern with a displacement antinode at each end and a displacement node in the middle. The distance between antinodes is always equal to 1/2 of the wavelength. And in this case, that is equal to the length L. So then you can write that particular relationship. The corresponding frequency is such that it is the velocity divided by 2L for an open pipe. And you can see here, fundamental frequency, the second harmonic, third harmonics. So figures, the second and third figures of what you see up here. So those two show the second and third harmonics, and their vibration patterns have 2 and 3 displacement nodes respectively. And you can see those here. For these patterns, the length L of the pipe is equal to 2 or 3 half wavelengths. So you can see that this is equal to L over 2 and L over 3 respectively. And the frequencies are twice or 3 times the fundamental frequency. So for every normal mode, the length L must be an integer number of half wavelengths, and the possible wavelengths are given here. Corresponding frequencies you can solve for. So all the normal mode frequencies for the pipe that is open at both ends is given by this particular formula. Obviously for frequency, it's given in hertz. When n is equal to 1, that's going to be your fundamental frequency. And obviously V is going to be the speed of sound in the air. Now, here in figure 12.24, we're going to show a stopped pipe, open at the left but closed at the right. The distance between a node and the antinode is always going to be 1/4 of a wavelength. So we can see here the fundamental frequency. We're going to get a third harmonic of this, if this situation develops where we have, instead of just the quarter of a wavelength, we have 3/4 of a wavelength, and then 5/4 of a wavelength. So this is 1/2 the fundamental frequency for an open pipe of the same length. The pitch of a stopped pipe is 1 octave lower, factor of 2 in frequency, than the pitch of an open pipe of the same length. So figure 2.24b shows the next mode for which the length of the pipe is 3/4, corresponding to a frequency of 3. Here it's going to be a frequency of 5 times the fundamental. So if you look at that, the lengths and how the wavelengths are associated is given by this, or given by this particular formula for a stopped pipe. And only odd values of n are allowed for this.